Hello, welcome to this class. In this class, we will go through last set of exercises in the NCERT. Okay, so we are going to go through 1.9 to 1.17. So that will be like 9 questions, right? 9 questions. So let's go to the disclaimer slide. The images, text, and other materials used in our presentations are for educational purposes only. We respect the intellectual property rights of the original creators and owners. If you are the owner and have any concerns or issues, please contact us at sathi@iitk.ac.in and we shall remove the content immediately. Please note that the parts of the content may have been generated using generative AI, which is experimental. So this is question 9, exercise 1.9. The photograph of a house occupies an area of 1.75 centimeter square on a 35 mm slide. The slide is projected onto a screen and the area of the house on the screen is 1.55 meter square. What is the linear magnification of the projector screen arrangement? Okay, so there is a photograph of a house on a slide. Okay, there is a photograph of a house on a slide. On the slide, the house has the image has 1.75 centimeter square area, and on the projector, when it is projected, it has an area of 1.55 meter square. Okay, and they are asking for linear magnification. They are not asking for area magnification. So that keep that in mind. Okay. So I will give you guys 10 seconds. Okay. So let's go to the answer slide. So area of the house on the slide, that is given. It is given value here and given value. So it is 1.75 centimeter square. So it is, we return at we again mentioned that on the solution side. Okay, and the area of the image on the formed on the screen or on the projector. Okay, which is 1.55 meter square. Okay, we have to find the magnification. We need to change the unit, right? Either make this 1.75 centimeter square to meter square or make this into centimeter square. So we did the second option, which is more easier to calculate. Yes, so let's see the next line, that is aerial magnification equal to area of image of divided by area of the object. Okay, here object is not a real house. Object is the image on the slide. Okay, and area of the image means actually what is being projected on the projector. Okay, so it is 1.55 into 10 raised to 4 centimeter square divided by 1.75 centimeter square. Centimeter square will cancel because both are same. So we will get what? We will get they haven't given us the answer in that. Okay, so actually its root will be equal to 94.11 because this is aerial magnification. We need what? Linear magnification. So linear magnification will be root of aerial magnification. That's why we are getting answer as 94.1. okay, actually here 94.11 hai. The answer is actually 94.11, but we know that we have to take care of significant figures. In this chapter, the first line of the exercise, it is said that every answer you should consider significant figures. Okay, so in the this 1.55 and 1.75 ratio, the number of significant figure on the numerator is 3 and denominator is 3. So we the answer should have the least significant number of significant figures which the ratio numerator or denominator have. So here both are 3, so the answer should be 94.1. okay, we need to round it off 94.11. in this there are 4 significant figures, we need to make it to 3, so that's why the answer is 94.1. is it clear, anyone, everyone? Okay, so let's go to the next question. Okay, so this is a very interesting question. State the number of significant figures in the following. Okay, so there are A, B, C, D, 6, right? Yes, 6 numbers are numericals are given, and asking us how many significant figures in each number has. Okay, each figure has. Okay, so how many significant figures in this option? First question, first part A. Could you please type it in chat box? Okay, someone is saying 3. Some people are saying 1. Okay, the answer is actually 1. Okay, the significant the zeros after a decimal actually are insignificant. Okay, if there was a non-zero instead of this 0, if there was a non-zero number, then the zero between the zeros between the decimal point and 7 would have been significant, because this is also 0 and there is a decimal point, and this is there is no non-zero before the zeros, because of that these are insignificant. Okay, and what about the option part B? How many significant figures are there in part B? Yes, part B 3 is correct answer. And part C. Part C, there is a 0 after decimal point. Yes, part C has 4 significant figures. Very good. Part D. Yes, part D also has 4 significant figures. Part E. Yes, it is also has 4 significant figures, same as E. F also has 4 significant figures. Let's see the reasons. Okay. Okay, the given quantity is 0.007 meter square. If the number is less than 1, then all zeros on the right of decimal point but left to the first non-zero are insignificant. Okay, that means if the number is less than 1, so 0.007 is less than 1. Okay, all zero on the right of the decimal point. So on the right of decimal point, what are they? This is the right of the decimal point. Okay, but left to the first non-zero, left to the what is the first non-zero value here? 7. So left to the non-zero and after the decimal point. Here there are two zeros like that. Okay, both are insignificant. This means that here two zeros after the decimal are not significant. Hence only 7 is a significant figure in this quantity. Okay, so the number of significant figure is 1. Okay, let's say there are 3 more zeros after this 7. Then how many significant figures are there? Okay, imagine my number is 0.07. After that 3 more zeros. Then how many significant figures are there? Yes, 4 actually. 7 plus 3 zeros. 4 significant figures will be there in that case. Okay, so let's go to the part B. Okay, so the given quantity is 2.64 into 10 raised to 24 kilogram. Okay, here the power of 10 is irrelevant. Okay, for the determination of significant figures. Okay, hence all the digits 264 are significant figures, so the number of significant figures is 3. Okay, what about C? The given quantity is 0.2370 gram per centimeter cube. Okay, for the number with the decimals, the trailing zeros are significant. That means the zeros after 7 are actually significant. Hence the besides digit 2, 3 and 7 0 that appears after the decimal point is also significant figure. So number of significant figure is 4 actually here. Okay, so this 0 is actually significant. Okay, is it clear? Let's say that there is a 2 zeros after this decimal point. Then how many significant figures will be there? 0.002370. Okay, yeah, then the significant figure number doesn't change. It will still be 4. Okay, because for a value which is less than 1, the zeros after decimal point and left to the non-zero, first non-zero will be insignificant. Okay, let's go to the part D of the solution. Okay, here it is joule, so it is a energy. It can be potential energy or kinetic energy. Okay, for a number with the decimals, the trailing zeros are significant. Okay, so the given quantity are all digits are significant figures. Okay, have you wondered why these zeros after point are significant, decimal point are significant? Okay, the zeros after the decimal point actually signifies the it signifies the precision of the measurement. Okay, 6 joule and 6.00 joule are different. In 6 joule there are only significant figure 1. Okay, so by mentioning 6 joule we are saying that there might be plus or minus 0.5 joule error will be there, right? Answer can be the value can be 6.5 joule or 5.5 joule. Okay, so that's what 6 joule actually means. But if the answer is saying 6.00 joule, there can be only what 0.005 joule error. Okay, so the 6.00 means it can have values 6.00 005 or 5 point some. You have to subtract it. Okay, is it clear? The more zeros after a decimal point actually signifies the precision of the measurement. Okay. Hello. Is it clear? Let's go to the part E. Okay. The given quantity is 6.032. Right. In this also significant figures is 4. Okay. So all zeros between two non-zero digits are always significant. Okay. Important point. All zeros between two non-zero digits are always significant. So number of significant figures here are 4. All the digits are significant. Okay. Okay. Let's go to the part E of the question. Actually solution part. So here also there are 3 zeros which are between decimal point and first non-zero digit. So these first 3 zeros are actually insignificant. So here also number of significant figures are 4. This zero is actually significant because it is between two non-zero digits, right? So if the number is less than 1, then the zeros on the right of the decimal point but left to the first non-zero are insignificant. That like we said said that in part A of this same question. Hence all 3 zeros appearing before 6 are not significant figures. All zeros between two non-zero digits are always significant. Hence the remaining 4 digits are significant figures. Okay. Okay, let's go to the next question. I hope it is clear to everyone. Okay, let's go to the next question. Okay, so this is 1.11. Okay, exercise 1.11. The length, breadth and thickness of a rectangular sheet of metal are 4.234 meter, 1.005 meter and 2.01 centimeter respectively. Give the area and volume of the sheet to correct significant figures. Okay, so it is again easy question. So let's I will give you guys 10 seconds. So just have to remember the that significant figure in the answer should be least of the equation, right? Least in the left side. What should I say? You know what I mean. Okay. So length equal to breadth equal to, okay. Okay. So what we are doing is, instead of changing this into centimeter, we are changing 2.01 centimeter to meter. Okay. So this has 4 significant figures. This also has 4 significant figures, but H has only 3 significant figures. Thickness. Okay. Thickness has only 3. So both volume and area should have only 3 significant figures in the final answer. Before that, actually, you can do all the calculation with all the full number. Okay. But in the last step, you should round it off to 3 significant figures. Okay. So we again tabled it. So quantity L significant figures, number of significant figures is 4. B has also 4. H or thickness has only 3. Okay. So how to find the area? Area here means surface area, right? Surface area. So 2 into L into B plus B into H plus B H into L, right? That will be the formula in finding the surface area. Okay, that I have already mentioned that the answer should have only 3 significant figures in the final answer. Okay. So surface area is 2 into L into B plus B into H plus H into L, right? In a even though it is a sheet, you can actually imagine a cube or cube like shape. So it will have L into B on the both sides, B into H on the both sides, and H into L on the both sides, opposite sides. So that's how we do the and we substitute the values. Cuboid. Okay. So actually, if you do this calculation, it will have 4 significant figures. But we know that the answer should have only 3. So we rounded it to 8.72. Okay. Okay. Now volume of sheet. Again, L into B into H. Just substitute the values. So it has what it has 3 significant figures. This 0 is not significant. Okay. Okay. That. So this number has only 3 significant figures, i.e. 8, 5 and 5. Okay. So I think you all know this basic idea. Okay. Let's go to the next question. This question was very easy, right? Okay. So mass of a box measured by grosser's balance. Okay. So there is a box. It has 2.30 kilogram. 2 gold pieces of masses 20.15 gram and 20.17 gram are added to the box. Okay. What is part A? The total mass of the box. B. The difference in the masses of the pieces to correct significant figures. Okay. Okay. So I will give you guys 10 seconds. So let's go to the solution slide. So even though in the question it is mentioned that significant figures, when we are adding or subtracting numbers, the decimal point, the number, the keeping the same number after decimal point actually plays more important role. Okay. So let's start here. So mass of gold is 20.15 gram. To make it to kilogram, divide by 1000. So we will get 0.02015 kilogram. Okay. And piece 2 will have this value. Okay. So 2.30. If you add, you will get 2.34 kilogram. Okay. It is actually keeping up with the significant figure. Here significant figure is 3. Here it is 4. Here also 4. Okay. But the point is, in addition, the final result should retain as many decimal places as there are in the number with the least decimal places. Okay. Hence, the total mass of the box is 2.34 kilogram. So, in case of adding this kind of same dimensions, the more than significant figures, we have to take care of number of decimal places first. Okay. Decimal places takes importance, priority. Okay. In this kind of cases. Okay. Is it clear? So in here, number of decimal places is 2. There are 2 digits after decimal. here what, how many, like 5, here also 5, but the least number of decimal places is 2, so answer should also have 2 values after decimal place only, or should have only 2 after a point. Okay, so here also finding the value, the 20.17 has 2 decimal places, 20.15 has 2 decimal places, so here answer should have only 2 decimal places. If you think about a significant figure, here there are 4 significant figures, here there are 4 significant figures, right? So answer should be of 4 significant figures, but we don't do that, because in case of addition and subtraction, we give importance, priority to this idea, like the decimal places before and after the calculation should be same. Okay, is it clear? Okay, so let's go to the next question. Okay, this is 1.13. Okay, a famous relation in physics relates moving mass m to the rest mass m0 of a particle in terms of its speed v and speed of light c. This relation first arose as a consequence of special relativity due to Albert Einstein. But due to Albert Einstein, yeah, he discovered special relativity. A boy recalls the relation almost correctly but forgets where to put the constant c. So he writes the equation m equal to m0 divided by 1 minus v square all raised to 1 by 2. That means this whole term is under the root. Guess where to put the missing c. Okay. Okay. So you guys have already found the answer, but we have to go through the answer. Okay. Okay. So there is so much explanation here. So in this slide, we don't have the full answer. So what is the basic idea? The dimension on the left side and right side should be same, right? So on the dimension on the left side is m raised to 1, l raised to 0, d raised to 0. Okay. And there is also there is already one m0 here, so it will also have same dimension. So the denominator should be dimensionless. The denominator should be dimensionless. If the denominator is dimensionless, we will get the answer correct. So then again let's examine the denominator. So 1 minus v square by, so 1 has no dimension, so the v square this second term should also be dimensionless, right? We have already established the fact that if I add a plus b, a and b should have same dimension, or if we subtract a minus a from b, both a and b should have same dimension. So similarly, if one is dimensionless, the second term should also be dimensionless. This is only possible if the 1 c square comes as the denominator of v square, right? Okay. So we are just writing the dimensions. Okay. The dimension of light and dimension of speed of light and dimension of velocity, both are same. That we all know. So here, as I said, one is dimensionless, so second term should also be dimensionless, which will be only possible if the second term is v square by c square, right? And we can only add c. Okay, so we can only use c. We cannot use anything else. So that's why the final equation is m0 divided by 1 minus v square by c square all raised to 1 by 2. Okay. Okay. Is it clear, everybody? Okay, let's go to the next question. Okay. The unit of length convenient on the atomic scale is known as an angstrom. Okay, and is denoted by angstrom. 1 angstrom equal to 10 raised to minus 10 meter. The size of hydrogen atom is about 0.5 angstrom. Okay, what is the total atomic volume in meter cube of a mole of hydrogen atoms? Okay, so in the question they have given us that they have introduced us a new unit of length, which is angstrom, and angstrom is 10 raised to minus 10 meter. So angstrom is used to measure the size of atoms and molecules. Okay, and they have said that the size of hydrogen atom is 0.5 angstrom. So they haven't mentioned is it a radius or diameter. Okay, so usually in usual sense the size of a size of an atom or size of a molecule is given, it usually talks about radius, its radius. Okay, so this is actually a radius of an hydrogen atom. Okay, what is total atomic volume of one of a mole of hydrogen atom? So in a mole of hydrogen atom there are 6.023 into 10 to the power 23 atoms. So yeah, and you have to also keep in mind, we have to keep in mind significant figures. Okay, so radius has only one significant figure. Okay, so I will give you guys 10 seconds. So let's go to the solution slide. So radius is 0.5 angstrom, and that means 0.5 into 10 to the power minus 10 meter. And how many significant figure are there? One significant figure. Okay, so in the final answer should have only one significant figure. Okay, so we are going to find out volume of one hydrogen atom by doing we are actually assuming that it has a shape of sphere. Okay, we are assuming that hydrogen atom has a shape of sphere. Okay, so we plug the values and we get this answer. And 1 mole of hydrogen contains this many 6.0223 times 10 to the power 23 hydrogen atoms. So just multiply. So actually we will get a value which has more than one significant figure, but we round it off to this 3 into 10 to the power minus 7 meter cube. Okay, yeah. So somebody in the chat said 3.15 into 10 to the power minus 5. So 3.15, but we cannot take this 0.15 because in the as a starting point we have only one significant figure. So in the final answer should also have one significant figure. Okay. Okay, let's go to the next slide. Okay, next question. So next question is interesting. Okay, 1 mole of an ideal gas at standard temperature and pressure occupies 22.4 liter molar volume. Okay, what is the ratio of molar volume to the atomic volume of a mole of hydrogen if the radius of hydrogen atom is 0.5 angstrom? Okay, take the size of hydrogen molecule to be 1 angstrom. Why is this ratio so large? Okay, so you guys read it one time yourself. So in this question they haven't mentioned we have to find the ratio of molar volume to what atomic volume of hydrogen or molecular volume. See, what I mean is that in the previous question we actually found out the volume of Avogadro number of hydrogen atoms. Okay, there is also volume of Avogadro number of hydrogen molecules. Okay, so in this question they haven't mentioned which ratio should we take, right? What is the ratio of molar volume to the atomic volume of mole of hydrogen? Okay, if the radius of hydrogen atom. So in this they have said the mole of hydrogen. In this section they have said that mole of hydrogen, but they have given us a radius of hydrogen atom. Here they have given us that take the size of hydrogen molecule. Okay, so that's why I earlier told that this is a interesting question. So, and one thing I also mentioned that usually when it says that the size of some molecule is given, it is usually radius, but in this case it is not, because actually size of hydrogen molecule or diameter of an hydrogen H2 molecule is 0.78 angstrom. So how can it be radius of hydrogen molecule be 1 angstrom? See, this question has some confusing aspects about it. Okay, did you understand what I was trying to say? Okay, let's go to the solution. So what we did is we took even if it's a hydrogen molecule or a hydrogen atom, both have some kind of 0.5 angstrom radius. So we went like that. Okay, so here it is written radius of hydrogen atom. Even if it is hydrogen molecule, both are actually radius of hydrogen molecule, that is H2 is 0.39 angstrom. So almost the same. So again we assume that this atom is of a shape of a sphere, and just plug in the values. Okay, so volume of 1 mole will be 6.023 into the times 10 to the power 23 times 1 volume of 1 atom. Okay, or 1 molecule. So again we get a 3.16. Okay, so this is not our final answer, so you can actually write this. Our final answer is actually a ratio. Okay, so volume of 1 mole of hydrogen is at STP 22.4 liter, and 1 liter is 10 to the power minus 3 meter cube. So we do the calculation and we will get a 7.08 times 10 to the power 4. Okay. Okay. Hmm. Is there any mistake in our calculation? I think this is correct, right? And we have to think about the or keep significant figures in mind. So we started with the 0.5 angstrom. So our final answer, final ratio should have only one significant figure. That's why 7.08 we rounded it into 7, right? Hence the molar volume is 7 times 10, 7 into 10 raised to 4 times higher than the atomic volume. For this reason, the reason is the interatomic separation in hydrogen gas is much larger than the size of a hydrogen atom. Okay, because this value is, there is no in interatomic space between them. This is like we smushed it everything together, right? Compacted it into a cube. So usually that is not not what happens. There is space between each molecule, so that's why we have this big value. Okay, is it clear? Okay, let's go to the next question. Okay, explain this common observation clearly. If you look out the window of a fast moving train, the nearby trees, houses, etc. seem to move rapidly in a direction opposite to the train's motion. But the distant objects, hilltops, the moon, the stars, etc., seem to be stationary. In fact, since you are aware that you are moving, this distant object seems to move with you. Okay? You might have felt it all this also, right? When you travel on a train or even a bus, these hilltops, yeah, they tend to move with us, right? Uh, like even big towers, like high towers, when you look through the window, they seem to move with us. So what is the reason? Okay, I will give you guys 10 seconds. Okay, so the reason is the parallax. Okay, so if you make a line, this is our solution. So let's see, line of sight is defined as an imaginary line joining an object and an observer's eye. When we observe nearby stationary objects such as trees, houses, etc., while sitting in a moving train, they appear to move rapidly in the opposite direction because the line of sight changes very rapidly. Okay. On the other hand, distant objects such as trees, stars, etc., appear stationary because the larger distance because of the large distance. Sorry. As a result, the line of sight does not change its direction rapidly. Okay. So let's say, okay. So I am here. No, this is imagine that this is a tree. Okay, and you are here in a train, and you moved here. Okay, So this is the angle subtended. Okay. Okay. So imagine that this is like some hilltop, and it is very distant from your train. So the train is here. Okay. The this you travel the same time, so the distance moved will be same. Okay, this much distance, and it will be difficult for me to okay, you can imagine the theta formed in this condition will be very small, right? So that's why it feels that you don't feel the difference, because the angle is almost same. So you will feel that this object is actually moving with you. Okay, is it clear? Okay. Okay, 1.17, right? This is the last question, I think. The sun is a hot plasma, ionized matter, with its inner core at a temperature, with its inner core at a temperature exceeding 10 raised to 7 Kelvin. Okay, and its outer surface at a temperature about 6000 Kelvin. At these high temperatures, no substance remains in a solid or liquid phase. In what range do you expect the mass density of the sun to be? In the range of densities of solids, liquids, or gases. Okay, check your guess correct from the following data. Okay, repeat. Okay, let's after this question, let's go to the previous question again. Okay, if you have time. Okay, so they have given us what? They have given us the total mass of sun, the radius of sun, and what they are asking us, what will be its density range? Will it be in the range of solids like iron, etc., or liquids or gases? Okay, so we know that for water our density is 1000 kilogram per meter cube, so we have to check. And for iron and everything, like it is like 5000, 10,000, like, right? So we know the density ranges of solid, liquid, and gases. So by we can compare it, and we can find what is the density of the sun. Okay, in which is the density of sun in which which is in which range, right? Okay. Okay. So this is again very easy question. Even if we get the significant figure wrong, it doesn't matter, because the answer is not about any numerical value is not asked in here. Okay, so mass is given, and you all know density is mass by volume. So radius is given, and volume of sun again taking it as a sphere 4 by 3 pi r cube. Okay, so we do the calculation. Okay, and this is the volume of the sun. Okay, so mass by volume, we will get 1.4 into 10 to the power 3. So it is very close to our water density. So we can say that density of sun is in range of what? Density of liquids or even solids. Okay, so even though the temperature is the sun is not sun is a hot plasma. Okay, so it is actually not liquid or gas or anything, right? It should have a density which is lower than gas. That is the thing we understand from here, because the temperature is so high, it should have a density lower than the density of a gas, but it has a density which is comparable to solid. Why is that? Because, could you please tell that in chat? Why it has a density which is comparable to solid? So even though it should have a density which should be lower than gases. It is because high gravitational attraction of the sun to its mass. Yeah. The density of sun is density or range of solids and liquid. This high density is attributed to the intense gravitational attraction of the inner layers on the outer layers of the sun. Okay. So inner line attracts the outer layers towards itself. That's why it has such a high density. Okay. Is it clear? Okay.